apologies if you can hear my neighbor mowing his lawn in the background. Um, I can hear it quite loudly. Um, Today I thought we would do a practical example of the sensitivity analysis we talked about yesterday. Um, I had some trouble uploading the yesterday's lecture to Canvas. It was giving me an error. I think I figured it out how to import it from YouTube. Uh, so if you had trouble viewing it, let me know, and I'll try to look into that. I posted the homework, the next homework. I graded most of the intermediate reports. They're looking good. I like where we are there. I've got 3 more to grade today. Those will be done today, guaranteed. um, and then, yeah, I think that's it, announcement-wise. So let's take a look at the example. This example comes from the Wilson book that is the typical book um, for this class that is no longer in print. Um, but it's a nice little exploration of shadow price and sensitivity analysis in general. So I thought we could take a look at it. Unless anyone has some questions that they want me to talk about before this. Okay. So, they have this problem. They set up this problem, this radio manufacturing problem. Um, we're paying people $5 an hour to work 40 hours a week or 50 hours a week. I guess we're not in a well-regulated labor environment. Um, but it's a cute little problem that will give us a good view of practical ways we can think about sensitivity analysis. I did notice one issue. I think this 2 should be a 1 here. Is my I don't know if my cursor shows up. C'est la vie. There's a slight error in the table. I corrected it. Well, it's a discrepancy between the table and the LP they give. So what I did is I wrote this up in my Mathematica format that I have, and I wrote out all of the different parts of the profit coefficients that they have. So in the table, radio 1 sells for $25, costs $2, and costs 3 hours of labor total, which is $5 an hour for laborer 1, $6 an hour for laborer 2. I subtracted that all out and got the same LP that they give in the book. Once I corrected that issue in the table. So that's as far as I've gotten with this problem. I thought we could explore it here live. So it doesn't give us, well, it asks us what is the value of the price of a Type 1 radio. Okay, for what values of the price of a Type 1 radio would the current basis remain optimal? That's the first question. So I did find, I did solve it and put it in the optimal basis so that we can look at it. So the question is, for what price of radio 1 is this still optimal? Well, we still have a positive value for x1 if we does the current basis remain optimal? Okay. So let's explore that. Let's change the price. Let's bring it down to 23. See what happens. We're still on the same basis. No, we're not. We're no longer producing any of radio 1. So I guess I didn't explain what the problem was. We're producing two different types of radios with different labor costs, and we want to see, oh, well, we want to maximize profit. Excuse me. So just messing around with it, we're seeing that we're not in an optimal basis anymore. No. Well, correction. We might be in a degenerate basis. So x1, x2 is the basis that the tableau is in. We notice that it has the same objective function value. So what if we swapped out x1 for s2? We land with the same objective function value still. So we have multiple optima at $23 for radio 1. I suspect if we drop it down to 22, yeah, S2 X1 or X2 is optimal. X1 is no longer optimal if it's in the basis because it doesn't make us any money when we its profit margin is 0. So it's no longer worth producing. Interesting. Okay. So how can we see originally it was 25, so how could we see that maybe 23 is not, or is going to be as low as we can go? Maybe we should get the dual. Maybe we should get the dual of this. So that's going to be y1, y2. And it was 40 y1 and 50 y2. This is a minimization. The transpose of that A matrix, well, that A matrix is symmetric. So I think the transpose That's just itself. All we have to do is put in our dual variables. I'm going to call this dual. Okay, so there we have the dual. It gives us the same value as the primal when our cost is 25. So it tells me we probably did it correctly. Okay, so this is a minimization problem, so we would be looking for, okay, did I invert something? Oh, okay. So the initial basis S1, S2 is infeasible. You can see that with -3, -2. So I guess we pivot, and we know that from the solver that the basis is y1, y2. So let's get those in here. Yeah, that's feasible, and it has the same objective function value. So we can see complementary slackness. Here, S1 and S2 were 1/3, 4/3. In the dual, Y1, Y2 are 1/3, 4/3. Or the reduced cost of the slack in the primal is the same as the value of the dual variables in the dual. And similarly, the slack, reduced cost of the slack is the negative of the value of the primal. Why is that negative? Is that the case for all minimizations? Did I do some math wrong yesterday? Did I forget to do that? That would make sense because we shouldn't ever have a negative in the right-hand side column, otherwise we're infeasible. But if we have a positive in the reduced cost row for a minimization, then that means we're not optimal. So I suppose that if we're converting a minimize to a maximize, or a minimize has a maximize dual, and the reduced cost row will be the negative of the value row for the value column for the primal. That makes sense to me. I might have to go check my math because I didn't include that yesterday in our lecture. So in both functions, or in both LPs, the slack is non-basic. So that means changing any of the constraints is going to alter the optimal value. We're not altering the constraints yet, we're just altering the price. What if I drop this down by one? How does this change? Okay. So that went up from 1/3 to 2/3. Yeah. We moved a third from S2 over to S1 for every... Well, we'd moved 2/3 over. So 24, we have 2/3. We're increasing, so when we dropped $1 in profit for radio 1, we increased slack 1, but we decreased slack 2. So slack 2 is going to be our problem. We decreased it by 2/3. Or, well, we halved its value. It was 4/3, now it's 2/3. So if we bring it down to 23 like we had before, brings it down again to 0 like we noticed before, and we have multiple optimal solutions. Can we see that? Okay, so when we change the objective function value in the original problem, when we reduce this to 2, okay, actually, yeah, let me do this. S1, S2. So here we start with um, in fact, let's get one more in the mix. So if we pivot in x2 first, we end up with a 1 here, and a 2 here, and we are subtracting something. Right, we divide this row by 3, to get this row. And then we subtract this row from this row, or this row from this row, which would get us 4/3. Because 2 is 6/3. So if we had 24 here, we have a 2 there. We subtract an additional 1. So I suppose we can see this relationship in this case. In this case, it works out that we can see this is the number we are subtracting from this number every time we increase or decrease the cost or the price of radio 1. That should have to do with C transpose AB inverse A. If C transpose AB inverse A or that's CB transpose AB inverse A, right? That's from our what do you call it? Canonical form equation. I wonder if we can, let's try to compute that for this problem actually. I'm getting interested now. Mistake. I'm going to spend all my time on part 1 of this. Ooh. I want a blank document here. Whoop. Why did it do that? Landscape. And why is the PDF not showing up? Great. Put it behind me. Okay. So if I look at the problem, I have that A is 1, 2, 2, 1, that. AB for our basis x1, x2, AB is 1, 2, 2, 1. AB inverse is excellent question. What is the inverse for that? That's complicated. Negative 1/3, 2/3, 2/3, negative 1/3. And we're going to let C be, we're going to let that be 3 plus delta. And 2. And we're going to see how that delta affects things. So CB transpose AB inverse AN is 3 plus delta 2 negative 1/3, 2/3, 2/3, negative 1/3 AN is the identity matrix. So we are left with a vector negative 1 minus 1/3 delta plus 4/3 and 2/3 plus correction, not 2/3. 3 times 2/3 is 6/3, which is 2. Plus 2/3 delta minus 2/3 is going to be negative, no, it's 1/3 minus 1/3 delta and 4/3 minus or plus 2/3 delta. I think I got some negatives wrong. Oh, that's the issue. I actually think I want minus delta. There we go. Um, and so we see that if delta equals 2, then we get 1, 0, which would be our result. So that's how you can tell how far you can change the objective function coefficients before we change feasibility. You add a delta to it, and then find the canonical form, and then solve for delta. Or solve for delta at whatever equals 0. In case anyone cared. Great. So we did that. We answered A. We could answer B in precisely the same way. We would just add the delta or subtract the delta from the second coefficient. And now maybe we'll do something worth thinking about. So if laborer 1 were willing to work only 30 hours per week, would the current basis remain optimal? Well, let's throw that in. So laborer 1 was working 40 hours a week. Let's let him work 30 instead. Let's get rid of these. We don't need this. So it looks like it's still optimal. The solver is still giving the same value as our tableau for that basis. So it looks like 30 hours is still optimal. And here I can tell you how we can see that in the dual. So here, this negative 20 is the reduced cost for constraint 2 or for constraint 1 in this dual function. It's the negative 20 is the shadow price for the dual constraint 1. Constraint 1 corresponds to the first objective. No, hold on. I'm all sorts of confused. Huh. What about if we drop it to 20? Okay. So if we dropped it to 20, then our basis is different. And we're infeasible in our original basis. Okay, well I'm slightly confused. Okay, so 25 hours for whatever reason seems to be the cutoff. the degeneracy. Yeah. So that's the allowable decrease in constraint 2. Well, that's constraint 1. Yeah, the allowable decrease in constraint 1 is 15, which is not showing up in the dual. How is that supposed to be computed? I'm not remembering. I thought it was the reduced cost of the slack in the dual. No, the reduced cost of the slack in the dual is the value of the optimal, of the decision variables in the primal. I suppose you could do what we did over here. Let's see if this works. We could take B and add a delta, subtract a delta. B was originally 3, I'm looking at the dual, it was originally 40, 40, and 50. I'm going to subtract a delta, and then take AB inverse B, not transpose. One-third delta plus 100 over 3 and then 80 over 3 minus 2/3 delta minus 50 over 3 is going to give us 60 over 3, which is 20 minus 1/3 delta, or plus 1/3 delta. And 80 minus 50 is 30 over 3 is 10. minus 2/3 delta, and then I'm going to solve this for that equals 0, is delta equals 10 times 3/2 is 15. And that's our allowable decrease. Okay. So that is a way to compute allowable decrease. Or increase, I suppose. So if we wanted to know how far we could increase it, we could solve so decreasing the first value of b doesn't affect, well, it will continually increase the first value of b prime, which won't give us an infeasibility issue. If we were to add, if we were to increase 40 to, say, 50 or 60, we'd have to, we would get a subtraction here. So if delta, so let me solve the other one. Delta equals negative 20 over, or no, negative 20 times 3 is 60. So if I upped that to 100, we would get a 0. And here, let's try that out. 100 gets us 0 there. 101. 101 makes us infeasible. Or not infeasible. Yes, infeasible. In that basis. Cool. Figured that one out. It was originally 40. Nope, I'm editing the wrong entry. 40. There we go. Back to our original thing. We could do the same thing for the second constraint to find its allowable increase or decrease. I'm not going to do that. I'm just going to plug in 60 like the problem asks and see. And that looks like it's still optimal. What about 70? Still good. 80. 80 is about where it becomes degenerate. So 90 should be infeasible. Yep. Infeasible. Cool. So its allowable increase is 30, just from guessing and checking. We should get the same result if we did our minus delta trick again. The last thing is to find the shadow price of each constraint. To find that, we're just going to look at the reduced cost for the slacks, or the values of the dual variables. Either one, they give the same result. We get that we would pay $1/3 more an hour for laborer 1, correction. If we were to pay $1/3 more an hour, we would break even. So let's try that. Come up here. Guy 1, 5 is 15/3, so 16/3. Let's try 16/3. What does that do? Huh. So at 16/3, we're getting 220 divided by 3. What's the decimal of that? 73 1/3. Okay. So what if we were to bump it up to an additional one? We're still getting the same basis. Oh, I think I see the issue. I did not change it over here. 16 over there. There we are. Now our shadow cost is 0. That's it. So at this point, we're still profiting. We're still making $66 from this plan. But we would, if we were to pay laborer 1 any more, we're going to change the basis. In fact, we already have, that's strange. Yeah, we already have a multiple optimal solutions. So we could change this and put S1 in the basis and have the same solution. So if we were to bump this up again to 17/3, suddenly we're no longer optimal at what our basis was. Actually, let's bring it back down to 15. So the shadow price then indicates that we would be willing to pay 1/3 of $1 extra to get more of this resource. So in this problem, the resources, the constraints, correspond to how much each laborer is willing to work, how many hours, and our shadow price is how much we would be willing to pay to get more of that resource without losing money. So I think that's all we're looking for here in this problem. I think that's all I wanted to talk about as well. So does anyone have any questions about other things? Any other questions about the course, about the content, about the project, about the homework? Any other questions? Alright. If not, I'm going to end the recording and you guys are free to go.